and an organizer, but also a great mentor to all of us. Okay, so I also wanted to say Katrin said sorry she couldn't make it, and happy birthday. Okay, so what I'm talking about today is joint work with, well, me or her, depending on who was supposed to give this talk, and Fourier coefficients of meromorphic modular forms. So the goal is to talk about Fourier coefficients of negative weight meromorphic modular forms, and to see how they're different than for holomorphic modular forms or weakly holomorphic modular forms, which have been studied in great detail. And to embed the entire question into a larger framework. So to look at the question by putting it into a bigger space and understanding that bigger space and the bigger story. So you might say, well, if we really want to know about meromorphic modular forms, why do we look at a bigger space? Well, the problem is in negative weight, you don't know that anything necessary. If you just give me the principal parts, if you just give me kind of where are the poles and what order they have, you don't know that something actually exists there. So how do you construct these things? Because you don't know they necessarily even exist if you just give me a random principal part. And so the idea is, by putting it in a larger framework, you can construct something more general that has arbitrary random principal parts, and then you can specify to the cases when it happens to be a meromorphic modular form. So by looking at a larger space, you can get some information. Okay. Looks like green doesn't show up very well here, sorry. So what are weakly holomorphic modular forms? Well, they satisfy modularity, they're holomorphic in the upper half plane, but we allow some growth towards the cusp, so that's what's different than, say, holomorphic modular forms. And a famous example is the partition generating function. So you take a partition generating function, and there should be minus there, you multiply q to the minus 1 over 24, and you get 1 divided by eta. And eta doesn't have any zeros in the upper half plane, so this is still holomorphic in the upper half plane. But as you go to infinity, eta vanishes, right? It's a cusp form. So 1 over eta has a pole at infinity. And so that's what we mean by weakly holomorphic. We allow, as you approach a cusp, that it's going to blow up because of the pole there. And Hardy and Ramanujan used the circle method, so generally complex analysis, but the circle method in particular, to get a nice asymptotic formula. So this is the kind of thing that we want to know about Fourier coefficients. How fast do they grow? Or, so how can we get the explicit value? So even just using this rough estimate, if you look at, say, the numbers of partitions of 200, you get this number, and this estimate is not too far off considering how big we're talking about here. Right, so even this first estimate is pretty good. But Ramanujan says, well, actually, if you do a little better, the error term goes to 0. And so you actually can get an infinite sum where you actually have equality here. And these AK ends are certain Klusterman sums. Now, Rademacher and Zuckerman said, actually, all weakly holomorphic modular forms, there's nothing really special about the partition generating function. If you look at this more general space, they all have this shape. But not what was asked in his thesis to look at the converse question. What if I have something that looks like this in the same way that these weakly holomorphic modular forms do? Is it true that I can go backwards? Is it necessary the coefficients of a weakly holomorphic modular form? And the answer, turns out, is no. So that's what I'm talking about when I say let's look at a more general space. So that leads us to something called the Mach theta functions. Now, one example that was given by Ramanujan is the f of q function, which has some connection to the rank differences between even and odd ranks of partitions. So this also has a combinatorial feeling. And if you think about it, this looks very much like a partition generating function. These pluses just become minuses. In Ramanujan's last letter to Hardy, he wrote 17 functions down and he said were the Mach theta functions. He said they're similar to theta functions being modular forms in his language, but they're not modular forms. He neither proved that they were not theta functions or explained how they were similar to theta functions. And he didn't really give a full definition, and unfortunately this was his last letter And he passed away shortly thereafter. This was unfortunate that he couldn't explain what he meant by this. Now, cut forward quite a bit later, and Zwegers put this into a more general space of what are called harmonic Moss forms, and it turns out these are what are called the holomorphic parts. So what Knock was looking at was the holomorphic part of a more general modular object. And these things have the same kind of coefficients as these Rademacher and Zuckerman expansions. What are harmonic Moss forms? Well, they still have modularity, but instead of being holomorphic, they're only real analytic, but luckily they satisfy a certain differential equation. In particular, they're annihilated by this operator. And so in the case that we're looking at, we're talking about -1/2, so kappa will be -1/2. So in integral weight, if I look at, say, k as a positive integer, there's a nice, this operator splits nicely into two pieces, where this C operator, if you look at it, if you think about anti-holomorphic differentiation, it annihilates meromorphic things, right? So one solution that's obvious that you get is that it will kill meromorphic things. But more will also be killed because sometimes this will send something to something that's meromorphic, and then the second operator will kill that. So in some sense, these harmonic things are sort of two steps away from being, they're sort of one step away, they're two steps away from being zero, or one step away from being meromorphic. So that's one way to think of this operator as sort of one step further away, so to say. And to just put that briefly, it sends these harmonic Moss forms to classical modular forms. So if you start out with classical modular forms, it's kind of a pre-image. And if you're lucky and kappa is an integer, I guess there should have been an integer there. If kappa is an integer, there's a second operator, which sends to weakly holomorphic modular forms. So the bang here is going to be weakly holomorphic. It's exclamation point. And the differentiation operator here is just regular differentiation. So repeated differentiation a certain number of times. And Bohl's identity is the identity that says that this is actually related to the raising operator. So this operator repeated many times turns out to be the same as the mass raising operator, which happily keeps modularity. So on one side, we have something meromorphic. On the other side, we have something modular, and they turn out to agree. That's what Bohl's identity basically says. A very famous example of a harmonic Moss form is from Herzbruch and Zagier. They defined the Eisenstein series. Sorry, there should be a sum here, of course. The generating function for the Hurwitz class numbers, plus an extra piece. So the Hurwitz class numbers generating function is not modular. But if we add this extra piece where theta is just the normal theta function, then suddenly it becomes a modular object. But we lose the holomorphicity, because this object is no longer holomorphic. And so that's the kind of thing that we're talking about when we say the completion of this object of the Mach theta functions. We add another piece like this, and we suddenly get something modular, but what we lose is holomorphicity. We lose the meromorphic property, but we gain modularity. And that allows us to kind of understand it. So because I had Q as either 2 pi I z, okay. So I just did it z there. But it's theta of W inside the integral. And this splits into two pieces. Again, there should be a sum here. One obvious piece is the meromorphic part, and what we call the holomorphic part, and the non-holomorphic part. In a very clear way, it splits here. And the non-holomorphic part can actually be written as an expansion in what are called incomplete gamma functions. So it's an incomplete gamma function times a power of q. And so in some sense, it has a very similar shape. And Zwegers did the same kind of construction for the Mach theta functions. He found that you can add an extra piece and get something really modular in the same kind of way. And if we look at the f of q that we saw before, this Mach theta function, now we understand that it's the coefficient of a certain form, and we have some kind of asymptotic for it, that Ramanujan conjecture, and Dragonet proved, well, that's true. She said that was true. And then Andrews extended that, and the two of them conjectured together this infinite sum. And then once it was understood from Sager's work that this fit into that more general framework, again we go back to Knopf, and we say this has the same kind of shape as one of these kinds of expansions that Rademacher looked at. Well, the key ingredient are Poincare series. Because these, you can force the principal part, the part that grows towards infinity, you can force it in a certain way by picking this theta in a nice way. So you kind of pick a typical Fourier coefficient that gives the kind of growth q to the minus m for some fixed m. And so for the partition generating function, for instance, it would be q to the minus 1, because you have minus 1 over 24. And then by Poisson summation, you get the Fourier expansion of this, and the holomorphic part looks like the Rademacher expansion. So each of these has an expansion that looks like the Rademacher expansion. And again, the point is that to write a general form in negative weight as a linear combination of these, this infinite sum might look ugly, but you only care about the part coming from the constant. The constant here is the only thing that really matters, the constant here. And these same Poincare series occurred recently in Gannon's proof of Matteo moonshine. So these things keep reappearing. Okay, so now we're going to switch gears, and we're going to say, what about looking at Fourier coefficients of something else? Well, let's look at meromorphic modular forms. So we have now something that's meromorphic, so now I'm going to allow it to blow up at some points in the upper half plane. And if it's positive weight, we force it to vanish towards infinity. If it's negative weight, it's like a constant towards infinity. But let's essentially just assume it's vanishing towards infinity. And actually, this story goes back as far as the partition function. Hardy and Ramanujan looked at 1 over E6. Well, E6 vanishes at I. So this has a pole at I, just like 1 over eta has a pole at infinity. And what they did was they used the circle method to get the expansion of this. And then Ramanujan also conjectured an expansion for 1 over E4 and some others as well. Now Bernd Bialek, I think it was correctly pronounced to me by Professor Bernd today, and Adjayi, they again used the circle method and proved all of Ramanujan's conjectures, and they also had some second order poles. So 1 over E6 has a first order pole, 1 over E4 has a first order pole. There are also some in there where they have second order poles, and they had to do a lot more work because the computations for the circle method become quite complicated as the order increases. So they did really a very good job of getting the expansion and seeing that they had the same kind of pattern coming up over and over again. In another direction, Peterson looked at the same question, but only assuming simple poles, and he looked at the question using Poincare series instead of the circle method. And he was able to get, he wrote it differently than Ramanujan. So we kind of want to get the same kind of expansion as Ramanujan had, of Hardy and Ramanujan's first expansion. But he had a slightly different one. He said actually this expansion of Ramanujan is the same as plugging in a point to some positive weight Poincare series. So it turned out that these expansions just look like Poincare series. So, well, Poincare series, again, it's just the same kind of this function that we mentioned before. So what are the coefficients of 1 over E4? Well, they grow very fast. But if you think about it, they have to. Now, why do I say they have to? Well, if the expansion converged everywhere, then in particular, the function couldn't have any poles, because it would expand right past that pole. So there has to be a radius of convergence. And if there's a radius of convergence, the coefficients must exponentially grow at a very explicit rate. So the constant term, actually, in this case, is not too hard to figure out. But to get that infinite sum is a lot more work. So the basic idea that you see these coefficients growing quite fast, and you can also see it's going to alternate forever. And you'll see that in a moment from the expansion. So Ramanujan conjectured, and then Bialek proved in his thesis, that 1 over E4 has an expansion like this, where the beta n, well, I write it essentially the way that he wrote it. So 6 over E6 of rho. So remember, this is 1 over E4, and there's sort of interesting E6 of rho showing up. The sum over lambda, and then the sum over solution CD of this, where lambda is things that are norms c squared minus cd plus d squared. And so c and d are going to be solutions to lambda equals this. So these are all possible lambdas that could occur as solutions. And then we take all solutions modulo some kind of distinct property. So CD and DC, we kind of consider them to be the same. And actually, you can see that that's going to come actually from multiplication in Q adjoining rho, multiplying by rho or power of rho or something like this, or -1. So that all these kind of what we call distinct comes from sort of modding out by that relation. And this h sub CD, well, the first term is minus 1 to the n over 2. Now remember, I said that it's going to keep alternating forever. Why do I know that? Well, I know that because this turns out to be the main term, because I have this exponential here. I said there should be exponential growth. Well, we see it explicitly in this sum. And the exponential growth, it's divided by lambda, so if we have solutions, these are going to have higher orders, and we see that very fast the main term is going to be always this one. N doesn't have to get very large before you see that this wins. So you see the alternation already. And then this HCD for further terms is some sort of cosine or something. And 1 over E6 had the same basic shape. So also these other examples had the same basic shape. So Berndt, Bialek, and Yi found the second order one, and they related it to a first order one. And you could see that they had the same shape. So you've got to ask, well, is this something more general? So I'm going to use, when I use this one, this is also a Z, but I'm going to call it Z. So this is Z, and the other Z is Z. My explanation for that is this is a Gothic German Z, so I think it's probably okay to do that. So Z sub 2 is the imaginary part, and Z sub 1 is the real part. And we get an expansion like this, where these C sub k's are essentially the cosines that showed up from before. So these are these h's that showed up from before. Now we're going to sum over ideals in Q adjoins Z. So we're factoring out by this idea of distinct that Ramanujan wrote down in a slightly different way, but I think this is what he meant. And then this lambda becomes the norm of the ideal, and the star here just means primitive ideals. So since Z is going to be I or rho in our cases, this is nice. It's just simply principal ideals because that's all that exists in this field. And so we get sort of nice things. And 1 over E4 and 1 over E6 have shapes like this, where Z is rho or Z is I. So 1 over E4, we see where the pole is, and 1 over E6, we see where the pole is. And it turns out that if the poles are at I or rho, then no matter what the order is, they always have this shape. And of course, that's only true for sufficiently large imaginary part because there's a radius of convergence. So when we talk about the Fourier expansions, we're only talking about the Fourier expansions near infinity. Otherwise, they don't make sense. And actually, there's a similar statement when Z is not I or rho, but then we don't have this thing with ideals necessarily. It doesn't quite work out the same. But essentially, they have the same shape. You factor out with the same kind of identity. Except there's really nothing to factor out in that case because there's no units when we're not having an elliptic fixed point. So it looks a little nicer for elliptic fixed points, but the basic picture is the same for all. Okay, so let's go back to the way Peterson looked at things. So what did he look at when he looked at these forms? He called them H sub 2k. Well, he called it minus 2k. the weight is what they called the negative dimension at the time. And 1 over 1 minus e to the 2 pi I z minus z. So when z is z, this becomes 1 minus 1, and you see there's a pull. So he forces the pull. And the nice thing is that this thing, well, first of all, it's a Poincare series in z, so it's modular in z of weight 2k, necessarily. But what about z? Well, we know it has a pull at z equals z, but what else do we know? We know it's meromorphic as a function of z, is z and z. So in both variables, it's meromorphic. But it's not modular. And actually, that was exactly what Peterson used. He used the fact that it wasn't modular to figure out when it was modular, he would get a meromorphic modular form. So he figured out exactly what conditions were necessary to make it modular, which linear combinations were modular. And this comes from a condition that's forced by the Riemann-Roch theorem. And this allowed him to determine all negative weight meromorphic modular forms. And then actually you can get higher order poles by differentiating in z. Because we don't really care about z, we care about z. We want negative weight. And so somehow this is allowing us to pass from positive weight to negative weight. And to do that, we apply some differential operators in z, and then we don't care about the fact that it's no longer meromorphic in z, it's still meromorphic in z. But actually, we can complete it by taking a linear combination with some other forms. There should be a bar here. There should be a bar here over the z, sorry. I think there's a bar here over the z. Otherwise, this would be 0. So we add this extra piece. So again, going back to what happened with the Mach theta functions, you add this extra piece, and suddenly it's modular in both variables simultaneously.
R also should be 1, right?
What's that?
Your index R in the sum should be sort of 1.
Yeah, I'm not sure about that. There's a z bar here. 0 is still.
Yours term, it's a 0 term. You repeat it twice.
This should have a conjugation over the. There's a typo there. Sorry. Yeah. And z goes to this hk hat. It's what we call polar harmonic of weight 2 minus 2k. Well, what do I mean by that? I mean that it's like a harmonic Moss form, but it's allowed to have poles in the upper half plane, not just at infinity. So we extend the definition of harmonic Moss form to allow poles in the upper half plane. And again, if we apply differential operators in z, this is going to still be a harmonic object. So we get a polar harmonic Moss form now with higher order poles, because every time we differentiate it in z, the order in z goes up of the poles. So we end up constructing something that's a polar harmonic Moss form, and then we rewrite the holomorphic part of this. So now we split this into two pieces. It's Fourier expansion, we can split it into two pieces, a holomorphic part and a non-holomorphic part. And the holomorphic part we write as linear combinations of these functions. And now if it happens to be that this linear combination that we take is a meromorphic modular form, then it's also equal to its meromorphic part. So instead of looking at what Peterson did, taking something that's necessarily meromorphic and asking when it's modular, we take something that's necessarily modular and ask when we take linear combinations, when is it meromorphic? So we reverse the question of what Peterson looked at. And then we compute the Fourier coefficients of these h's, and those are exactly these f, k, j, r's that showed up before. I think r in this case is something like k minus j or something like that, something explicit. I'm also going to mention that Ramanujan looked at E2 over E6, E2 squared over E6, and E2 over 4. So these are, again, not modular objects, but they are quasi-modular objects, so we allow multiplication by arbitrary powers of E2. And using similar methods, you can actually show that these also have expansions of the same shape, meaning that they also have expansions in these f functions that I mentioned before. So future questions might be, well, what about looking at something like 1 over E2? Now this is not only not modular, it's not modular in a really bad way. So E2 is very close to a modular object. But if we put it in the denominator, we can't add something to make it modular anymore. So this might be an interesting question, and actually it was already looked at by Sevar and Sevar. They showed that it's what's called an equivariant form. So they kind of put it in some kind of space, but maybe they don't have modularity properties. So maybe we can put it in some kind of thing where we can understand it in a different way, and then maybe try to answer the question for this as well. And that's all I have. Thank you.
Thank you very much. And are there any questions or remarks?
I'm sorry for being late. As soon as I went out, I had to sit with Margaret to solve a technical problem.
It's okay. Always the organizer.
If not, then I guess we can continue then according to the schedule in 2 minutes. With the talk of Kane, and then after the talk, the lunch, and after the lunch at 1:30.